Okay, so ladies and gentlemen, thank you for coming back. So let's say I have made a small announcement via the Zalo group, but basically what we are going to do is we will have an an examination for 1 hour in combination with the empirical project, and each component will account for 50% of the final evaluation results, right? So this is something a little bit of a change, but I would say as I was preparing the scripts, one of my worry is that if we do not try to give some effort in getting used to the commands, we probably will forget everything by the time we finish the course. So that would be necessary, and I think I hope that you all will support, right? So let's say all the time up until now, our approach is that we want to use Python to support us with some calculation. So it is always very important that we have to know what we are aiming at, what we want to compute. And once we know what we want to compute, we will be able to answer the question how to compute it. And once we get to know how to compute it, we will be able to apply that into Python. So that's the approach that we have taken so far, right? So now, in order to make it clear to the whole class, I will say individual project will be 50%, right? So individual project that would be determined later when we have the final 2 sessions on after you have the examination of the course by Professor Mehdi Hossein Kocha. Okay. The final examination will account for 50%, and it will be determined based on the announcement of the secretary, right? So let's say this is something is for your benefit that we have an additional evaluation method in order to make sure that we all benefit from the effort that we have exerted so far. So let's say last time we stopped at we were kind of working on and struggling a little bit with how to implement the variance covariance matrix. So we will start from there, and we will continue to follow the course plan that we have set out, right? So let's say many of these topics seems to not have been covered yet, right? But let's say they are the simple extension of the mathematical derivations that we have learned so far. So for example, if we understand the math, then the GOS is just a simple step, the GMM and the panel. So we are going to cover that for the whole, I mean, hopefully by the end of today, all of these topics will be covered. Tomorrow, we will devote the whole day into optimization. Right? That is, what is it? I'm sorry. Sorry. And then tomorrow, okay. Tomorrow we will spend our time on replicating, and I'm sorry, on the optimization problems, right? So it will be one day. Hopefully, if we finish all of that, the linear issues today, tomorrow will be a whole day talking about optimization mathematically, and optimization with the econometric applications. Good. So after that, we have a day off on Wednesday, and on Thursday and Friday, we will discuss this topic. Right. So there will be a lot to do here. Um, there is an open secret that I cannot hide, is that all of the codes to replicate the paper has been uploaded to the publisher's website, right? So, but the code are in Stata. So by requirement these days, if we publish a paper, the original data that we get from the producer must be uploaded, and the code that we wrote in order to estimate that must also be supplied. So you can always have access to the data online. That's something I cannot I cannot prevent. Let's say we have to do it in Python. We cannot go to that and do it in I keep doing it in Stata. As like I said before, in the end, a professional academic would need both a combination of something like Python or MATLAB, and with an ACAM package like Stata or Eevee, right? So in this case, we are focusing our developing a set of skills to work with the kind of computational skills that we will need as we proceed with our work or with our future career in research, and also with processing complex um, data structures. So let's say for Friday, Thursday and Friday, we focus on this one. And these two topics here, your presentation and the like, will be done after you have before you have the in-person examination, right? So we will arrange someday before that. For example, uh, during Medi's course, what you are going to do, you will focus your analysis on topics regarding the financial markets, right? And then you continue to use Python. So your skills can only be improved, but not be deteriorated. After you sit in Medi's course, we will continue with the um, presentation, right? With the presentation, we will need a full day for your 1.5 day for your presentation, and then we will have um, the 2 weeks for you to write the project and submit it. So that's what we are going to do. After that, you have to submit it. Or let's say I will be flexible here. So let's say if after say you have the examination for maybe on when is it? 13th, right? So we will have the presentation somewhere on the 15th or so, right? On the 15th or so. And then you have the examination on the 25th. That is in-person examination, and you will submit your project about 1 week after that. Yeah, yeah, yeah. So the presentation is part of the project, right? So you keep working on it, and then No, no, it will not be right. It will be after you sit in the examination of maybe, right? So we will fix a date on that. But let's say you will have about after maybe examination, you will have about 3 days to work on the project or work on the data, and then you present it. I will give and your friends will give the comment. You write it up, right? That's the idea. So let's say the presentation is a component that is incorporated into the project, right? So there will be a rubric. So there will be the component on your presentation, how many points that you get on that. And in the end, it will be evaluated as a whole project. So that I will not only look at your submitted papers, but also on your presentation and how you contribute to your peers during the presentation, right? Good. Now, so with that, let's move on, right? Let's move on with last time when we were, let's say, so now in the slide set, I have uploaded the second set of slides. So please have a look at that. So we will continue a little bit with the set of slides that we had last week today, and then we move on with the set of slides that um, I have just uploaded. Right. So so basically we will. Sorry for the. I have just included the slides for the second part. I think it was not there when I checked, so it is now online. Right, so let's say section 2 will also begin with a lot of computation, right? Let's say um, I hope that you will in the end have some feeling that programming involves a lot of derivations. Programming only starts when we already have the solution to the problem at hand, right? So we need a lot of discussion on the methods, how we can come up with the final expression of the results so that we can code into Python. So a lot of theories here. I would try to go quickly through it, but basically the idea is that we need to derive the results before we can move on with any coding in the with Python, right? So last time we already talked about we were here, right? So we were at the place when we were talking about the regression table of in Python, right? So let's open the Python's let's open Spider and have a look at the problem we were dealing with before we stopped last week. Okay, so last week we were somewhere here and we were kind of saying how to get the covariance matrix and display it in a way that is beautiful and discernible, right? We don't want to have a jungle of numbers. Actually, I don't know. We has some solution, but after some trial and error, I decided that maybe the best solution is to export it to Excel. Because even if I use the heat map suggestion, when we have too many variables, it would not work. It would not work. So let's say let's run the model again, right? So let's run the model again. Let's see how much we have any change that we have implemented, so that we can be on the same page. So this is the version of the heat map that I thought could be of help. But when it is very beautiful when we have a small number of variables, but it becomes tedious when we have too many variables. So let's say basically last week we extracted a set of variables from the data set. Then we estimated for the matrix X of independent variables of 11 variables. Now I create the X2 during the class or not yet. So actually what we are doing now, let's say for the sake of the next hour or so, I have created the matrix X2, and matrix X2 is more or less like matrix X1, but I reduce the number of independent variables so that it could be easier in terms of displaying the results. So can you all please now manually, right, code the regression? Of course, I think everyone can do it now, but let's say just to instill in your head how to code the model, right? So let's say now define the matrix X2 in this way, right, and add a constant to it, and then estimate and run the regression of y on X2 for me, please. Yeah. So I is it my computer? I think so, right? That's this is I reinstall my Windows during the weekend, and this is now giving sounds that good. Okay. I want to. Okay, so can you all please run the regression, and then we will now, as promised, we are going to manually compute all of the regression results. As we said before, right? So Okay, the sound now is gone, right? So let's say it is an open secret, so I already presented it here, right? With the code that I have presented there, right? So what I want you to notice is when we started with the OLS model in Python, we often define X as the explanatory variable and Y as the dependent variable. But actually, if you notice, I have included a line here, and you can use the library and you can input the dependent variable and the independent variable similar to the way that you would do in Stata. Yeah, so let's say you don't even need to define Y if you want to bring it directly in. You don't even need to define axis if you want to bring it directly in. The difference between Python and Stata is that in Stata you have one and only one data set in the memory at a time. In Python you have many more data points, so data frames. So you have to specify the data frame that you are using. That's basically. So technically, if the data frames are of the same dimension, you can run a regression model that with variables coming from different data frames, different data sets. That's something I want to stand here. So can you all have, could you have all run the model 2, right? So it's ready, right? Let's move on. Right, let's move on. So now computing the computing the coefficient is too easy now, right? Everyone knows. So how we are going to proceed here? Let's say I will go to each point, show us how we can recover the data from the results from Python memory, and then we will do that manually. Right? So let's say for the estimated models, if you want to get certain basic results, you just, for example, you print it based on the model that you name and then the subcomponent. If you put print model, because here you name it model, right? If you name it Hà, then you have to put Hà, right? Then it is para, that is parameter. If it is co-para, here is a covariance matrix, and so on. So later on, we will see that, right? So for example, if we want to extract the matrix or a vector out of my Python memory, you will have to use, you just define it in this way, right? And then here we have the covariance to Excel. I did try to do a little bit of printing the, I mean, my ambition was to print the matrix in a way that is beautiful. But let's say basically after some trial and error, I think I have shared the function. It's better that we extract the matrix to Excel, and from there we can do the formatting ourselves, right? So for example, here is the covariance matrix that I have extracted to Excel, right? So let's say you see that with the Excel file, we can, for example, what we can do, actually, I can start typing the information in a more constant, in a more a more transparent way, a more explicit way, log of total income, then corruptible households, ethnicity, married, right? If the head of household is married, and household size, household size, this is one, right? Two members. Household size, this is three member. So let's say now if we do this, the message that I'm going to give you is when you have to do something that is for publishing purposes, Excel sometimes help. Let's say many times when we want to have a beautiful table, then it's better that we do it with Excel because that's my experience over the years. See, so we can also have the variance covariance matrix in this way, right? So this is of course we can format the number of decimal points that we want to show. For example, here, if we just say we go back here and say okay, so let's say here, if we just say like we want to have only 2 decimal points, right? Let's say put it into number and then 2 decimal points. Okay, so let's say when we have the variance covariance matrix, the probability that it has a very small value is there because the variance sometimes can be very small, right? So like the standard error can be bigger, but the variance is always very small because when you take the square root of something that is small, it will be bigger. That's something you already know, right? Okay. So just make it a little bit smaller. You see that here, now we have the variance covariance matrix with the variance on the diagonal. And of the diagonal, you have the covariance of the coefficient of log of total income with say, let's make it a little bit smaller and that you will see what is there, right? Now you see. Now, for this one and this one, you see that they are the same because this is the covariance between the coefficient of log of income and corruptible and corruptible household. Log of income, constant, right? Log of income and log of income here with the constant, and here the constant with log of income. Now, corruptible households with a constant, corruptible households with income, here corruptible households with a log of income. Now, my question to you is, this is not an econometric class, but let's say you must have a sense of it. How many coefficients that you estimated? For how many values can you estimate for the log of total income? How many? How many value could you estimate? Yep. Of the coefficient of log of income? One, right? Yeah. One. So how can you have the covariance? I cannot have a covariance of 5 and 6. You don't get it, right? So how can you get, so let's say when you run the regression model, right? You get the coefficient of log of income equal to 0.7. The coefficients of corruptible households equal to, let's say, 0.5. Right? Two value. Is that correct? How can you have the covariance of two values? How can the covariance be defined? The formula, but that's the problem, right? It must be intuitively explained. Why do you have the covariance here?
You mean like why we have non-zero covariance here?
Right. Because
okay. So like you want to show the relationship to variables?
no, I'm asking you guys. How can we have the covariance of an estimated coefficient that has only one value? Think of it. Think of it here, right? So you are saying that you have the covariance of the coefficient, right? How many coefficients for each of them? How many coefficients did you get? Do you get one? Right? You have one, right? It is shown. It is shown in the table. So how can you have the covariance?
Not just this.
That is not with the x. This is the covariance between the betas. This is the variance covariance of the beta. It has nothing to do with the x. Is that right? Now let's make sense of it. Let's make sense of it here. No, this is not a covariance of the axis. Is that right, Mingguan? It is the variance covariance of the beta. Right? So let's say when we do this, we have to, that's one of the most important thing when we learn about programming. In order to program correctly, you must really truly understand what you're doing. So this is a variance covariance matrix of is it correct? Oh, come on. Of the betas, not of the axis. Is that right? So with the axis, you have the rows and the columns that you can calculate the variance covariance, but this is not. Right? So how can we deal with that? How can we explain that? Now, Mr. Khánh Linh, do you understand how? Let's see if Khánh Linh, do you get? Are you better now, Khánh Linh?
I'm trying.
You're fine. Good. So okay. So let's say my question is, can you explain why do we have that? Covariance, right? Hello. Can you explain?
I think we can compute it by using covariance matrix and then time it with a sigma square
Right.
hat.
Yeah, that's the question. How to do that in Python, right? I agree. I agree that that's how we should do. But my question is, why do we have the covariance? Because you can estimate only one value. Is that correct?
Yeah.
Yeah. So that's my question to you guys is, this is variance covariance. Right. So let's say we have the variance covariance of beta. Beta hat. So that is how the beta, let's say, the indication here of the variance covariance matrix. Let me change the sound to the so let's say Khánh Linh, now the sound will be connected to the speaker, so the whole class can hear you, right? Okay. Can you say something?
Yeah, I also hear.
Okay, good. Everyone can hear you. Good. Now, my question to you guys is, why do we have the covariance, right, of the coefficients of corruptible households with the coefficient of married. The invariance, covariance here is say corruptible households with the household size is 0.00001. There is kind of indication that you know that the coefficient will be larger if this one is also large, right? So let's say if the coefficient of a household is larger, the coefficient of corruptible households is also larger. So, but you can only estimate one. So why do we have the covariance? If I want, let's say this way, I want to ask Mr. Thanh Huy, say, Thanh Huy, can you give me the covariance of x and y? And then I give you x equal 5, y equal 4. What are you going to do? I'll tell you, Thanh Huy, can you compute the covariance of x and y? X equal 4, y equal 5. What can you do? The mean is itself because you have one observation only. You take it minus the mean is gone. Right? Is that correct? So you cannot compute. Right? So here you have the coefficient. So this is for food for thought, okay? You think at home. You think at home. Why do you have the covariance? Aha. So you say that
This had like that being created because of the x in the formula. Yeah, and then we that like there are variables that can go together, I guess. Like there's some color.
Okay, so let's say I'm briefly explain, and then you have to catch up later, right? So let's say here all of the results here are expectation. That is to say, so what do we mean by expectation? Now, when we say that the expectation of beta hat, now it comes from here. It comes from here, ladies and gentlemen. It comes from the issue here, right? Let me take the smallest one and say now I erase this. Yeah. Now let's say here we often kind of confidently write expectation of beta hat given x is equal to beta. Is that correct? Is that correct, right? So what do we mean when we write this way? What do you mean when you write this way? Right? So these are the things that you have to. So what is an expectation?
We expect the beta that we calculate.
No, that's not what we expect. That's not what we want. No, that's not. The idea is statistically, right? If the sample size goes to infinity, you will get the estimated result that is equal to the true result. Is that right? That's the explanation. Right? So the expectation here means the mean. The mean value of beta hat. If you have the sample goes to infinity, then the mean value of beta hat will be equal to beta. Why there is a mean here? Pardon? One way is that you have different samples, but here I have one sample only. Yeah, one way to have different samples, that's correct. And you let the number of samples go to infinity. Each sample gives you one value, is that right? You sum them all, divided by the number of samples. The randomness cancel out each other, and you get the true value. Right? That is one way of explanation. Right? Here I have only one sample. Yeah, so this is something You have to think about. But let's say if you write beta hat is equal to x transpose x to the minus 1 x transpose y, right? X transpose y. Now I'm leading you to a simulation problem later. Simulation problem later. Now, so how can I write? Now, just this is something to be honest, I thought that I got it through to you during the pre-master course. But I mean, when I was teaching to the bachelor, and after a lot of teaching, one student came to me in a very serious manner. I don't get the expectation. And he asked, he keep pushing me exactly what Ming was. I would say, okay, because when you have many samples, you take the average. The average will be equal to the true value because each time you can get a randomness, right? But the randomness means that they can be bigger or smaller, and in the end, the randomness will automatically cancel out if you have many samples. And that's a very smart one of the best students in the class. She asked, she followed, but this is only one x. I said, then let the x go to infinity. She said, okay, but can you show me how it goes to infinity? It will be expectation. That's a very tough student. And I mean, I started for some minutes, and I said, okay, let's do it this way. Then this is something that you should do. So let's say you get it.
We have one equation. It's not like that we have one sample. The way that we have the right to choose as many samples as we want. Like we can choose one sample.
Right.
Individuals. At the same time, we can also choose a finite sample, but we can do it multiple times.
Right.
That is the meaning of this
expectation, right? But let's say when we have one sample, how can I show the student, or how can you show me that the expectation is a mean, right? Is a mean. Expectation is the mean when the sample goes to infinity. Right? Right? Okay. So let's say basically this is very simple. But let's say after some minutes I thought of it, let's rewrite the way. So when you want to multiply two matrices, what do you do? Now, when you have to multiply two matrices, what do? You have to find formula. You take the row, you times the column. Is that right? Okay, that's fine. That's okay, right? But let's say we can do it in a different way, and you understand the meaning of expectation here. Now, you have X as a matrix, right? Now I just extract one row of that matrix. One row is one observation. Is that right? Correct? Okay, so I will take it xt. So allow me to write xt here. So by xt, in this case, I mean a row of x. Okay, so I'm doing it in this way, right? I'm writing it this way. It is xt, but because xt, I write it in this way, I will violate my assumption, my convention in the beginning that whenever we write a matrix, a vector, it is a column, right? So I would put xt transpose here to tell you that this is a row. Fair enough? With me? Good? Okay, good. So this is a row. Yeah? Now, so there are two ways of multiplying a matrix, at least multiple ways, but at least this way will make it very easy to see. So instead of taking the first row times the first column, you have to you transpose x, right? You have the first actually the first column times the first column times the second column, but you have to transpose x. Now you don't do that, but instead you would do that x transpose x is equal to the summation of xt transpose for t equal to 1 to n. Okay, is that right? So by writing it this way, you are showing that this matrix is the summation of the contribution of each element, of each observation. Is that right? Because this one is a column by k times a row by k, it will be a k by k matrix. Is that right? And so for each observation, it will give you one matrix of k by k. And you are adding the k by k matrix of all observations into one. Is that right? So these are just simply two ways of doing the same thing. But this one will give you, so this is a contribution of one observation. And now I add the contribution of all observations, right? Okay, now, so I will borrow it. I will write 1 over n here. Okay, good. And then I write it 1 over n here. This is the mean contribution of each element, of each observation. Fair enough? Okay, so then I will continue to write expectation. So let beta hat is equal to 1 over n times summations of, now I will write it this way, right? So let's say summation of this is equal to x transpose x, but I write 1. So okay, now what I'm showing you is I will write it 1 over n summations of xt transpose, okay, to the minus 1, and then times 1 over n summation of xt yt. So beta hat consists of the contribution of each observation. Each observation will have one contribution. Now you take the average of that. So x and y vary, and there could be the randomness here. But if you allow the n to go to infinity, right? The n to go to infinity, this one, the randomness will cancel out. And it will converge to a constant matrix. Get me? Because this is the expectation of value, right? The expectation value is a constant. The true value. If you get a sample, there will be some randomness. But if you allow the sample to go to infinity, the randomness cancels out. And this matrix will approaches a constant matrix, right? If there is a relationship between x and y, is that right? This one will also converge to the true value. So when we take the expectation of beta given x, we are asking, on average, taking the contribution of all observations, okay, and taking the mean contribution of all observations, that would be equal to, so when that would be equal to the true value. So each observation will give you one contribution, but if you allow it to go to infinity, the contribution could contain the randomness. Sometimes it is too large, sometimes it is too small, but the randomness cancel out each other. Okay, by that I am invoking the so-called law of large number. Okay, good. So something like this. So let's say let's think of that. You know, so sometimes you just do it, and you say, yeah, because if I derive it, it will be x transpose x times sigma square. Is that right? Sigma square. The idea is, if you drop h and every time, every time you compute the value of beta, right? You drop one, you drop another one. So just randomly say, if you just randomly drop each observation once. So every time you drop one observation, you will have a new value of beta. Is that right?
Yeah.
Okay. And if you have all of that values of beta, you compute the covariance together. Get it? That's where it comes from.
I think it's easier to understand that, like, what the top student asks you something about this. I think it like come down to like different samples. So different beta also a random variable. So it can have
That's it, beta is random, right?
Yeah, it's not just one number. It's not one number, but depends on the sample.
Yeah. So this one number is the average that you get from that sample.
Yeah.
That one number, the one number that we have in the regression table, all of them are the number that you have taken the average of all observations, and you have the mean, right? So that's the reason behind. So basically, if you add, the question is how many different, for example, let's say we talk about, let's brainstorm a little bit about this one and we move forward. Now, for all of you, how many different coefficients of corruptible households can you estimate? How many, let's say, for example, a sample, right? N and k observation, k independent variables. How many coefficients of the, for each of the variables here, right? Just take one. Just take one. How many coefficients of this one can you estimate? No. Firstly, if you want to estimate it, you have to solve the equation, right? How many rows do we need to solve it?
How many observations we need to solve this one, right?
How many different values of that?
Like equal to the number of the.
Firstly, in order to solve it, you need to solve k equations, right? For k unknowns. So you need the first k observation to solve for one value of beta, let's say of the beta vector, right? And then from the observation k plus 1 till n, you can start doing the permutation, right? You can drop each of them once. Is that right? Or you can add them gradually, right? And then, so in the end, you have n minus k different values, right?
Why you have to just drop one or like.
But in the end, one is a combination of dropping three.
But we have like k plus 1, k plus 2, and k plus 3. But it is also different from k plus 1, k plus 2, and k plus 1. So like you say,
for sure. But
like it can be like a lot of numbers there. A lot, just not
talk about the permutation. Let's think about the way. Let's say we want to focus on the, let's think of the bootstrap idea, right? So every time you would drop one observation.
If we want it to be really exact, it's like we can choose from the size of n observation. Sample of k plus 1 observation from k, that is one version, k plus 2 R of n.
No, don't do that. No, don't do the permutation in that way. That would be a lot, right? No, let's say we want to draw n minus 1 from n. Okay, so that is the idea of bootstrapping, right? So you want to draw n minus k minus 1 from n minus k. So you will have n minus k way of forming. Because when you are drawing, let's say, if you want to draw k plus 1 observation only, that is, you are throwing away a lot of information and the volatility will be very large. Okay, So we just want to focus on the contribution of each observation. So we will draw n minus 1 from n. I'm sorry, n minus k minus 1 from n minus k, right? So there will be n minus k different values from that observation. So there is a lot of things linked together. That's why we have sigma square hat is equal to summation of e hat transpose e hat over n minus k. The same idea applies. Yeah. Okay. Good. So this is something sometimes people take for granted and just keep coding. Now, if we don't get the logic behind the coding, just is the coding, right? So we are the question when we have to code. A very important question that is constantly we have to raise is why we do this. What is the purpose, right? What is the purpose? Good. So let's say, of course, when we want to extract the diagonal, let's say 10 years ago, if people teach this kind of course, they would say you have to go to the manual and you try to learn how to get the diagonal elements of a matrix. And then you have to go to the manual and do it, right? Maybe when you started computer science, that's the way to go. But now you can go to ChatGPT, say, I have this matrix, give me Python code that extract only the diagonal. It will give you in no time. So ChatGPT is nothing more than a manual, but a very smart manual. Okay? And sometimes we can find things that we want. Sometimes we cannot, even if we are consulting a manual. So similar with ChatGPT, right? So let's say here is the way in order to get the diagonal element. So several ways I try to print, but let's say it just simply not it doesn't make a lot of sense. So just ignore about it. But let's say the idea of having an Excel file can be, let's say, to some extent easier to work with. For example, we have the heat map. When we have a lot of variables, it's like this one. It doesn't give a lot of information, but let's move on, right? Okay, so now we are going quickly. So beta hat we already did, and we are happy, right? Now we are going to compute all results of the regression table, right? So the beta is done. The fitted value. Now this is it's quite interesting. Now this is for you guys. You won't struggle. I know for sure. So you know from how to compute, except some of the guys who have been coding a lot. But let's say my question to you is: suppose that you already know how to compute the coefficient, right? So this is how you compute the coefficient. Now I need you to compute the fitted value. Now, can you do that? Fitted value is y hat. Now, can you compute the fitted value? We are on the same page. We define the x2, right? We have y, we have x2. Now, can you compute the fitted value with Python? The fitted value. Y hat. Now, it could be easy for you, but for some, it has some problem with. Now, I don't say it. Okay, can you all please start computing? Use ChatGPT, whatever you want, right? Just quickly. And it will give you weird answers, and you will start asking why so. Yeah. Quick. Now compute again. Build local. Thầy có đã share mất cái file này chưa đúng không? Chưa share đúng không? Dài đến đâu? Tôi làm thì nó không phải là 8.500 là đúng rồi. Vâng. Đó thầy biết ngay là làm là anh đang đi theo đúng trình tự và rất thông minh. Ok, cứ đi đi. Đi đi nó cái vấn đề nó nảy sinh ra. Làm nhanh là mình có rất nhiều cái value phải compute rồi. Tại thời điểm nào bạn nào cần trà để thầy tiếp nào? Chiều à? Ra chưa Huy? Đến beta đúng không? Ra chưa kia này? Dễ đúng không? Fitted value. Không thầy có bảo làm thế này đâu. Cái này fitted value bằng model dot fitted value thì dễ quá. Đó là built-in đúng không? Bây giờ em phải tính cho thầy bằng tay á, manually. Em phải code mà, đi ta học coding mà ta lại gọi từ trong bộ nhớ ra thì chơi gì? Nào. Nào em code cho thầy bằng tay nào. Nhanh nhanh nhanh, bây giờ bắt đầu vào giai đoạn hứng khởi rồi. Bây giờ ai code xong trước tiên sẽ có phần thưởng chẳng hạn, ví dụ 1+. Ok. Ra quay hát chưa? Ok. Anh không ra đúng không? Matrix not allowed. Đã huy ra chưa? Đang ra đúng không? Rồi. Ok, Chí Trung ra chưa em? Dùng chat GPT hỏi nó. Tao cần compute này nó ra liền. Nó ra liền xong mình sẽ hỏi xem là tại sao lại vậy. Dùng chat GPT nó ra liền. Thế anh ra chưa? À, sao em không cài được? No marginal name slash models hả?
Em có cài rồi nhưng mà tại sao nó không có chạy được nữa nhé.
Nó chưa cài đấy. Làm em copy này, em gõ PIP đi. PIP. PIP rồi, install.
Em cài rồi
Enter, paste, enter cả. Nó nói gì? You may need to restart the kernel. Okay. PIP 3 à? PIP 3. PIP 3. Rồi. À, nó không cho.
nhưng mà anyway
Nó bảo em phải restart cái kernel của em là phải chạy lại. Em vào đây khi mà nó vào console này. Em chọn restart kernel. Em chạy lại, em nhận.
File đó là em xài một remaster em để bắt đầu
Y hat equal to the model fitted value, right?
Right. And you got it? It's the same.
Yeah, it's
Okay, good. So Mộng Thiền got it done. Done Thư. Nó chết. Fine. Okay, fine. That's the manual. There's nothing to worry about. Get it? Okay.
nó bị lỗi cái label hay cái dimension của hai cái type khác nhau.
White hat. Thư.
Nó bị cấm với cái mục.
Thế xin lỗi.
Dạ, nên bật.
Xin lỗi.
Cái hình 2 để cho nó align được.
Để nó phải là cái gì? Ông đang nhân chia cộng trừ thì nó phải là cái gì? Đúng rồi, anh để nó là cái kia, nó không nhận là mấy kịch đúng không?
Ở trong cái license nó có cái label bên ngoài đó.
Đó. Rồi. Ok, đây là mình chỉ mắc những cái chỗ nhỏ nhỏ này thôi là mình làm được cả, đúng không? Bây giờ programming là gì? Ngày xưa programming nghĩa là biết cái vấn đề cần program, mở manual ra xem nó là cái gì rồi compute. Còn bây giờ là biết cái vấn đề cần compute, mở ChatGPT ra xem là cái gì rồi compute. Thế thôi. Như vậy thì suy cho cùng không biết là mình cần compute cái gì thì không biết học programming như thế nào được, đúng không? Rồi. Đan Thư có vấn đề gì không?
Tức là em không biết làm sao mà để thấy nó
Em mở ra thầy coi.
bằng với kênh
Quay hát của em bằng cái này, em chạy nó ra không? Em chạy đi. Ok. Ok. Em ra rồi, em ra được cái fitted value rồi đúng không? Rồi thế em muốn cái này thì đơn giản thôi. Bây giờ cái white hat em nhìn, em mở trên kia thầy coi đó là cái object nó là loại gì? Series đúng không?
Yeah.
White hat em click vào đó. Em double click vào đó. Đó, ở đây là đúng không? Vậy có mấy cách để ví dụ như là bạn Tuyền là bạn ấy print nó ngược lại thành cái cột để em so sánh đúng không? Bây giờ có một cách này, một cách bây giờ nó đang là nó đang làm bây giờ em print cùng một lúc cả white hat và fitted value đi, em print đi. Em print cái trên cái fitted value có chưa, em không gọi model dot print mở ngoặc ra, không sát vào model dot fitted value, model dot fitted value, dot là dấu chấm, fitted values sát vào em, sát vào values. Ok rồi, phải rồi, quay hát em chạy con ra cái gì? Nó sẽ print một ông ok được rồi. Bây giờ em gõ cho thầy YH bằng YH chấm chi nào. Tương dưới em gọi lên trên cũng được là YH bằng YH chấm T một cái. Rồi em print lại đi, em print lại đi. Cái dòng
Print
trên,
cái này.
dòng trên. Hả? Rồi em gặp trường hợp này đúng không? Em copy phần này vào ChatGPT, em bảo how to print both of them as columns. Khi mình gặp vấn đề này đúng không? Em copy cả cái chỗ này. Rồi, em lấy vào đây. Em bảo how to print both of them as columns. Columns xem ra gì? Nó đòi flatten ra đúng không? Cái là bay trừ. Khi mà nó là một cái array như vậy thì bây giờ cái dimension của nó phải được xác định là gì? Đó. Khi mà em flatten như thế này thì nó sẽ xác định cái dimension của nó. Comparison này. Nó đem nó bỏ cả hai cái đó vào một cái data frame đúng không? Rồi. Vậy thì cái này hơi dài dòng rồi. Em copy cái phần này em bỏ vào nó sẽ thành cái em sẽ print nó ra. Rồi.
Nó sẽ lỗi khó hơn khi mà phải tự tính beta hash nữa, chứ nếu mà lấy từ cái model là nó chạy được. Như Tú Tuyền là mình chạy ngon hơn là vì Tuyền dùng model param để lấy cái beta hash, còn nếu mà mình tự tính beta hash là nó không có biết.
Không được Tuyền làm vậy, là không được. Tuyền phải đi từ lấy beta h chưa tự mình tính ra cho thầy. Ok nào, tất cả cái thứ này phải manual, phải lấy cái beta h là mình tự tính ha. Nào các bạn nhìn là thầy không thể kéo xuống dưới được vì kéo xuống dưới lộ hết hàng, nhưng mà nhưng mà mỗi một dòng này nó sẽ là có phần là tự tính từ memory ra và một phần là tự tính bằng tay. Sau đấy mình sẽ gom tất cả những cái mình tự tính bằng tay thành một cái function, đó là cái function của mình đúng không? Đó. Nào nhưng mà bạn Lan Thư đã làm được một việc, cái là bạn ấy chuyển các cái số liệu của bạn ấy thành matrix đúng không? Lan Thư chạy thì rồi. Em copy cả cái đây em vứt vào. Copy vào. Tất cả mọi thứ phải manually. Em copy từ chỗ flatten đấy. Copy từ trên xuống dưới. Rồi, bỏ trên 5 pi đây. Đợi đưa rồi. Đó. Cái này tại sao mình sẽ ngồi mình ok em print nó ra nó sẽ ra ngay đúng không? Bây giờ mình sẽ ngồi mình hỏi câu hỏi của mình là thế thì cái việc mà chuyển mình cái đây cái kỹ năng mình sẽ program đúng không? Cái việc mà nó chuyển này thì pd chấm này để làm gì? Là nó khi mà em compute như thế này thì các cái object khác nhau có thể được tức là nó sẽ được ghi nhận bởi những cái object các kiểu khác nhau, ví dụ như là một cái series hay một cái matrix hay một cái vector đúng không? Vậy thì khi mà bỏ vào PD này hắn cần vớt tất cả thành một cái bảng như vậy Excel vậy đúng không nhỉ? Cái này hiểu bản chất của nó là vậy đúng không? Có nhiều cách làm khác nhau nhưng mà cho nên là bây giờ thầy mới nói là nếu mà không cooperate thì mỗi bạn hỏi ChatGPT sẽ cho một cái thứ khác nhau, khả năng rất cao là hai bạn cùng làm một vấn đề sẽ có cách tính khác nhau đúng không nhỉ? Để mà giống nhau trong cả ngàn dòng code mà giống nhau không thay đổi tí nào là rất khó. Ok. Examination thầy sẽ ví dụ như thầy sẽ đưa cho một cái matrix, thầy sẽ nói Ví dụ như thầy cho một cái regression, thầy sẽ yêu cầu là manually tính nó. Xong thầy ví dụ như thầy sẽ cho một câu khó, ví dụ như là hãy tính cái heterogeneity consistent variance covariance matrix, ví dụ là như vậy. Hay thầy sẽ nói là hãy implement cái test là biến 1, biến 2, biến 3 bằng là không có relevant trong cái mô hình này, đúng không? Bằng cả LR test, LM test và WOW test. Đấy. Vậy thì bây giờ các bạn thường làm rất là nhanh, đúng không? Ví dụ như cái biến này có quan trọng hay không, bây giờ các bạn có relevant không, các bạn nhìn vào các bảng regression các bạn thấy luôn, kết luận luôn. Nhưng đằng sau nó tính như thế nào bây giờ các bạn phải tính. Đúng không nhỉ? Đấy. Thì bữa nay rất nhanh nào. Bây giờ cái fitted value nào, các bạn làm hết chưa? Chung làm xong chưa, chạy được chưa? Chưa, khởi động lại nào. Nếu mà như thế này là thi lại điểm lại khó khăn rồi nào.
Nó cứ bị thế này.
Invalid syntax. Em tắt đi thầy này. Thầy xin lỗi. Rồi em vào đây. Thầy đoán là em để Python Anaconda đâu, em bỏ cho thầy Anaconda. Rồi. Yes. Rồi, chưa ra. Đợi lúc nào. Ok. Rồi, em lấy xong rồi em chạy từ đó. Rồi, khi nào nó chạy xong thì bảo thầy. Nào, cái chỗ như chỗ trí chung mà không install được ấy là khả năng rất cao là bạn mở, em không mở nó bằng administrator right, không nhỉ? Thì khi em viết nó không cho viết. Không cho viết. Hôm trước thầy nói ngay từ buổi đầu của lớp rồi. Ok, let's move on. Nào, bây giờ đây là các thầy đã làm và thầy không có thầy đã consult vài cái solution khác nhau trên Python trên ChatGPT, đúng không nhỉ? Và cuối cùng thì cái đoạn đầu tiên, nếu như mình mà muốn tính manually thì khi mà em compute beta h và em compute như thế này thì beta h, thì một câu hỏi đầu tiên cho các em là vậy cái object này nó là cái loại gì? Khi em chạy beta h như thế này, đúng không nhỉ? Thì vào đây variable explorer, đây thì lên chỗ beta h nào. Beta h ở đây là một cái matrix, đúng không? Một an array, đúng không? Đó, một cái object nó là một cái an array of đây là một cái matrix rồi nè. Tiếp theo nào, các bạn kéo dưới nào, một y bây giờ là gì ạ? Nào nhìn nào, y nào, y là series. Như vậy thì không thể nào mà em đem một cái matrix em nhân một cái series, đúng không nhỉ? Không thể đem một cái matrix nhân một cái series. Đó. Vậy thì bây giờ mình sẽ phải convert nó, thì có vài cách convert. Thì ví dụ như ở đây, one way to convert it is to use numpy.array y. So I also use the reshape here, and I included the reshape, the explanation for you guys. Right? So let's say basically one of the lessons we learned here is that you will not be able to make a computation if the components of an operation are of different types, right? So in this case, you have beta h as a matrix, right? But you have y as a series. So let's say there is a need to convert them into the one form of data. So when we use reshape -1 convert a one dimension array. Okay, a one dimension array here is a list into a 2D vector. So let's say when we do this one, we would say -1 here. The -1 tells NumPy to automatically calculate the number of rows based on the array length. You don't have to compute it. But then the column without -1, you would need to manually specify the number of rows, right? So let's say -1 here to say, I don't know how many rows. Just count it and make enough rows for me. And then the column is one column because it is one column. So let's say this is the explanation, right? So you change X2 into a matrix also, right? So let's say now you have Y1, Y is an array in NumPy, beta hat is an array in NumPy, X2 is an array in NumPy. So they are of the same type of object. They could be combined, right? So Y hat is X2 at beta hat, right? So let's say if we follow the normal wisdom, we just, because we already had beta hat here, right? So why don't we just keep going with Y hat? But let's say there is a need to convert the objects into the same type in NumPy before you start the calculation. Okay, so this is something you need to remember. Now, if we can compute the fitted value, then computing the residual is too easy. Is that right? So let's say you may see here that in the file that I will provide later, we start with the name, we do it with the memory, and then we compute it manually. Okay, good. Then you have residual. It's quite easy, right? Now, estimating the sigma hat square is easy, right? Sigma hat square. So sigma square hat is equal to E hat minus transpose times E hat. Is that correct? Over N minus K. So this is something we already know, right? So manually compute the okay, now it comes to, oh, I'm sorry. Now it comes to the variance covariance matrix, which is quite straightforward. Yes, give me a moment. The variance covariance matrix is not that an issue anymore, right? So let's say if you have the variance covariance matrix here, I put a variance matrix of our own. So it will be equal to this one. Yes. Question.
Just find that like usually type the formula for the beta and Y hat is like for the sake of the point of doing it manually, but like it lose one important thing from the model is that it's hard for us to call some beta because we cannot call them. We have to recalculate. This is 11. So we have to call beta hat 11 instead of, if we have the model, we can call model params and then you type the name of that variable. Yeah, but that's okay. Just a little bit more. Yeah, that would lose.
Not yet. So let's say now we compute it, and then our work is to put all of them into a function like OLS, and then from there we can call. So let's.
I mean, like if you calculate beta hat, I want to know the specific coefficients of, for example, like for x11, for example, you will not know that it is 11. I just say the name of like log of income, and you have to search for it on the table, but you don't have to do it if you have the model already. You do the function because you can say beta of that thing, but this one you cannot know which one is that one because you lose the label. Yeah, but that is okay.
Yeah. But let's say over here okay. So you mean if we want to call the coefficient of any of them, right?
Yeah.
Then you need to remember which one.
Yeah, but you cannot do anything with that except for like you have to manually search
in the Excel file again to count it.
But let's say I think now it's just to compute it. But when we put them into one we wrap them in one function, then there we have to put a dictionary of, right? So in a way, in the table, you will see the same, like we run it automatically. Is that correct? Okay, so the goal is now let's do the computation, and you will see that sometimes following the usual wisdom that it could cause a little bit of problem if we are not familiar with the computation. But let's say once we get to know it, then we can confidently move forward, right? Now for the standard error, right? The standard error, let's say it's easy to say that if you have a model, you print it, you get the standard error, right? But let's say if you do not know the standard error, it's also very simple. We already have the variance covariance matrix. That's right. So now we just take the diagonal of that matrix. We take the square root, we get it. Right? Okay, good. Can you do that on your own computer? Now, let's say this is what the difference will make. If you sit there, watch what I'm doing, in the exam, you would be in deep trouble. Right? Because you don't really have a real sense of coding it. Right? So I will not ask too far away from what we do in the class. But let's say at least you have to develop the sense of computing. Yeah. Okay. Now can we move faster, please? Otherwise, we will be run out of time, right? Now the T statistic. Now, so let's say it's fine, everyone, with the standard error. Now let's everyone is on the same page, right? I would allow everyone to. So I want to go to this point before we go to the T statistics, and I talk a little bit about distribution, right? Everyone have the right to repeat all of the computation so far. When you are happy, then we move forward, right? So let's say do the calculation up until now. Chí Trung is okay. It works now. Okay, good. So let's move on with the calculation, right? The variance matrix and the like up until here. Ồ, 10 giờ 41 rồi cả. Hoàn thế nhỉ? Làm nhanh nào. Phần lớn mà không chạy hết là thầy để cho làm ở nhà đấy. Xong chưa các bạn, xong hết chưa? Về sao các bạn xong hết xong thì thầy cần các bạn nhớ cho thầy một điều thế này. Thế là xong thì thầy nói. Rồi bây giờ mình được ra chơi nha. Mình được ra chơi tận 10 giờ 50. Với các bạn mà bận gõ thì ngồi lại gõ.
Thầy ơi, em xong rồi nha thầy.
À thế à? Cho em ra chơi 10 phút. Em có uống nước trà không thầy đưa này?
Dạ thôi được rồi thầy.
Thầy không cả đối đúng không? Mai đi học được chưa?
Dạ chắc là được á thầy.
Okay. Nếu mà mệt thì có thể nghỉ thêm nhá. Nhưng mà cố gắng ok chưa? Five rows cái gì đây?
Nãy em có bấm cho nó chạy.
Rồi em làm cái câu variance matrix. Mhm. Nhưng mà cái này là đang là từ máy nha, cái này là đang là nó đã chạy rồi, em gọi từ memory ra nha. Còn cái này ví dụ như cùng một cái đây, ví dụ như chỗ này ha, thầy lấy ví dụ đây là gọi từ máy ra đúng không, đây là tự tính đúng không. Cái này em làm chưa? Đấy, cái phần tự tính này là phải làm rất tốt ha, tức là bản chất của vấn đề chúng ta có cần cái này, chúng ta cần cái này này. Ok không anh? Đến đâu ạ? Bây giờ đúng không? Ok. Các program là phải trước hết phải biết cái toán đó là gì ạ? Là xong muốn làm cái toán này như thế nào để bảo ChatGPT nó bảo cho. Hay không mình làm mãi mình quen mình có một cái xem. Thì nó sẽ hiệu quả hơn. Kể cả ask ChatGPT cũng phải biết cách ask thì nó mới đưa đúng cái mình cả. Năm mươi rồi này. Let's move on, right? Let's continue. So let's say I want to borrow the example in the morning and to talk about something. And this will be something that is very much foundational. And I want you to, as we proceed today, to demonstrate the idea as we proceed. So let's say it's a very simple closed form solution of the OS model, right? And I ask you guys to write it in a way that it is equal to 1 over n summation of xt transpose to the minus 1 times 1 over n summation of xt yt. So actually the 1 over n here is to the minus 1 and the 1 over n here, they just simply cancel out each other. Good. So sorry. So the first intuition when we talk about the law of large number is that each observation will provide us with some information about x, and part of that is the randomness. Okay, randomness. So let's say if it is the randomness, let's take up the line like this one. This is the 2 beta, okay, or 2x. If it is the randomness, let's say I'm talking about the one dimension here. Sometimes it could be below. So it contains information about x plus some randomness, right? Sometimes it could be above. Okay, and if you keep moving a lot of points, when you sum them together, the randomness won't cancel out each other. Is that right? So when the sample size is too small, maybe the randomness is not it doesn't contain enough kind of varying randomness so that they can completely cancel out each other. But if you have a lot of points, a lot of data, the randomness will cancel out each other, and what you get is the true value. Get it? So this is a very simple. You want to let's think of a rice field. Rice field, right? Very much the image in Bến Tre. A rice field. You want to measure the height of each and every rice. every rice plant. So if you just take on one field, right? If you just take a corner of that, it could be different from the expected height of the rice plant. But if you allow the number of rice plants to be sampled to be very large, the randomness will cancel out each other, and in the end, you will have the expected value of the height of the rice plant, right? So that's the idea of the law of large number, right? The law of large number. So if you allow the sample to be very large, you take the mean of that sample, the mean will be closer and closer to the true mean. Okay, so when you have the samples that goes very large, we have the new concept. We say that the probability mean limit. Okay, so this is something you already know, right? Probability limit. So let's say that is to say the probability limit of 1 over n of xt, okay, won't approaches x bar or mu x. Okay, mu x is the true mean. So let's say you have the probability limit and you have the limit. So what is the difference between the probability limit and the limit? Now we are going to come to a result that is called consistency. Now what is the difference between the probability limit and the limit? So how can I imagine the limit and the probability limit? So the limit is to say if I have x approaches a, okay, in a line like this one, this is a, it could come from the right or from the left or from the right, right? It could come from the left or from the right. Now for the probability limit, it would not come from the left or would not come from the right. But it would, let's think of the probability limit as a distribution density. This, when the sample gets large, okay, the spread becomes smaller and smaller. I'm sorry, but let's say the idea is that one. So the distance between the largest value and the smallest value just becomes smaller and smaller when the sample gets large. So let's say when the sample is very large, you will not know. When the sample is very large, you will not know if this is the true value of beta hat, a beta. You would not know that it will be on the left or on the right. You will not know. But you know that the variance is shrinking. Okay? That's this conversion in probability. So I know that I do not know whether it will be smaller or larger, but I know the range is becoming smaller. Okay, so when the sample goes to infinity, I don't know what infinity is. Maybe Ming would know. Let's say that's the idea that is very large, right? The variance becomes 0, and the distribution degenerates into a point. So that there will be no variation anymore. So that is the idea of conversion in probability. The limit will have the sign, right? Approaching the limit from the left or from the right. The probability limit just doesn't care about that. It approaches from either side, but the only condition is that the variance is shrinking. And when the sample size goes to infinity, it degenerates into a point. So that is to say, when it degenerates into a point, we say that the probability limit of this sample mean is equal to the true mean. Okay, true mean. So why do we need to talk about probability limit? We need to talk about probability limit because of some special properties that the limit doesn't have. Let's say if you have the limit of, right? So let's say if you have in this case, what I want to say is this one, right? So, and then we talk about the distribution and we demonstrate the properties of the OOS with Python. That is another job of programming. But let's say if you have the limit of x as x approaches 0 is equal to 4. Let's say fx equal to 4. Okay. The limit of gx, another function as x approaches 0, is equal to 5. Or let's say there is no guarantee that the limit of fx times gx will be equal to 4 times 5. You don't have that. Or if you, let's say the limit of fx as x approaches a function, let's say a is different from the limit, or let's say the f of the limit of x as x approaches a. So those functions will not work, right? So you will not say, I have the limits of x, so now I put it into the g, the function. I get the limit of the function now. It is not. It is not okay. But the nice thing, this is, I'm talking about the limit. That's the thing that we study in the high school, right? The high school math. Now, the nice thing about the probability limit is probability limit of fx times gx, okay, as let's say n go to infinity, okay, it is equal to the probability limit of fx times probability limit of gx. So the probability limit allows this, okay, good. Or the similar, other similar thing, but let's say now if I take the probability limit, right? If I take the probability limit of beta hat, what do I have? So let's say beta hat is equal to x transpose x to the minus 1 x transpose y. It is equal to beta plus x transpose x to the minus 1 x transpose y. It is equal to beta plus 1 over n summation of xt transpose to the minus 1, okay, times some 1 over n summations of xt yt. Okay, now if I take the probability limit, what will happen? Okay, so let's say I will take the beta hat as the sample goes to infinity, right? It will be equal to beta, because this is a constant, I cannot do anything, plus the property limit of 1 over n xt transpose the minus 1, okay, then times probability limit of xt, I'm sorry, here it's epsilon t, right? Epsilon t, 1 over n here, summation of 1 over n xt epsilon t. Okay, good.
Thầy ơi, thầy không có present cái bảng nó lên đó thầy. Em đang xem cái spider, cái giao diện spider.
Oh, thầy quên. Thầy đang nghĩ là stress trên bảng tướng, được rồi. Thầy sẽ chụp cái ảnh gửi em. Ok. Rồi. Xong rồi, thầy chỉ lấy một chút ngắn này thôi. Okay, everything I'm telling you guys is, as the sample size go to infinity, this one will converge to a matrix that is constant, right? Because it is just the matrix of the x. If the x follow so-called IID, I will talk about that later. So this one will be something, a constant matrix. So let's say it will be S XX. It's a constant matrix. And if we assume that the covariance between x and epsilon is 0, meaning that the assumption number 3 is satisfied, this one will be 0. So S(x) is a constant matrix times something that is 0. In probability, this one will be 0. So probability limit, P limit of beta hat will be equal to beta. This is the result. But what can we see from here? What is the programming problem that we have to solve here? So when the sample size is not large enough, this one is nothing guaranteed that this one will be 0. Is that right? Is that correct? This one will converge to a constant matrix, fine. But if the sample size is not, the population mean, the expected value of this product is 0. But if the sample size is not large enough, it could be different from 0, right? So we can simulate a problem and to show that if we get the sample size become very large, the distribution of beta hat will concentrate on one point, meaning that we have to show somehow, some way that the distribution of beta hat just has the limiting that somewhere that is close to beta. Right? So this is the idea behind why do we say that the OLS model is consistent. So what do you mean by consistent? We mean that if we have more data, it will produce a better estimate. What do I mean by better? I mean by better, I mean it has a smaller variance. Okay, that is the idea of consistency. So how can we illustrate that going forward is another issue. Good. So a lot of ideas here will form a beautiful programming problem, right? Okay. Good. So I will go quickly here, and then I'm now coming back to the Python file link. So let's say the variance covariance is done, right? The standard error. So once we have the standard error, we can define the t-statistic, right? So let's say, so the t-statistic in the regression column, right? So how can we compute it? What is the purpose? Right? How do we compute that? And what is the purpose of that, right? So let's say in the now I'll talk about this a little bit later, right? Because we will need it for later computation. Okay. So why do we need to compute the t, right? Why do we need to compute the t? So the t here, right? In any regression table, we have the t statistic here. So what is it, right? It is the test statistic for the null hypothesis that the coefficient of the corresponding variable is not significantly different from 0. Is that correct? Remember that one? Okay. So how do we, let's say, how do we form that? So basically, if you want to compute that, just come here. So the t-statistics will be defined as equal to, right? So the t-statistic here will be defined as equal to, let's say tk, right? We already did that in many occasions. Tk will be equal to beta hk minus the hypothesized value. Let's call it beta here, right? Divided by the standard error of beta hk. Is that right? Okay, good. Now, ladies and gentlemen, if we are assuming we are worried that the coefficient here are actually 0, nothing more. But by randomness, we get it different from 0. We have to test it, right? We test it. So the idea of hypothesis testing, okay, I am worried that I hypothesize that it is equal to 0. So I replace it by 0 here. So I don't have to subtract anything actually. This is beta hat k divided by the standard error. That is why in the script file. We wrote it here. Is that right? Wrote it here, right? Okay. So sometimes I put the note there. So please read about it to understand more, right? So the T statistics, that is something we compute, right? So let's say I will be very brief here. I will be very brief here in terms of the distributions, and then we will move on. But let's say basically we have the normal distribution. So that is something we know already, right? The normal will allow you to, let's say, why is it called normal? Why is the distribution called normal? Now, Mr. Ming, why do we call it normal? Any idea? Now, Mr. Minh Quân, our mathematician, why do we call it normal? Because it was created by a mathematician Gauss, right? Is that right? Yeah.
Because any natural text is
because we normally we normally encounter it in our life. Okay, so it's everywhere. Right? Most of the natural and social quantities will follow some bell-shaped distribution. So we call it normal because we normally encounter it everywhere. That's it. Nothing more, right? So let's say it is a kind of a distribution. Let's think of the case when we talk about the height of the man in Vietnam. Right, a lot of people will be around the height of 165, right? Some will be more than 165, the other will be less. But if you measure the height of all Vietnamese, you create the histogram that we did last time, you would have something that of a bell shape. So that's why it follows a normal. So we know that the normal one have a bell-shaped curve, and the standard normal has a mean of 0 and standard deviation of 1. And the idea of standardizing everything you already know, right? Then we talk about the chi-square. The chi-square is, what is a chi-square? The chi-square is the sum. Now let's think of this is very important to make the inferences. The chi-square is the sum of a lot of standard normal random number square together, right? So when I square a standard normal number, what is the expectation of that square? Now, if I take z square, what is the expectation of z square? Now, what is the expectation of z square? That's it. That's the variance. If I take, now ladies, so what is the variance of a standard normal? If I take 1,000,000 standard normal, square it, what is the expected value of that sum of all of them? 1,000,000. Because each of them has an expected value of 1. I do it 1,000,000 and 1,000,000 one time. The randomness by the law of large number won't cancel out each other. I sum them together. I will get 1,000,000. Is that right? Fair enough? Chí Trung, get me? Not yet in anh say it again. Anh say it again, right? I say it again. Nothing to let's say, now let me explain this one. Now, then I will ask you to do the computation now. Let's say, okay. Đấy, uống này. À, nếu uống thuốc à? Now let me explain this one. So a chi-square. Now let's say the chi-square. So let's talk about it this way. People have the normal. You know what a normal is, right? The standard normal is a random number that has a mean 0 and standard deviation of 1. Variance is also 1, right? So people kind of thinking, maybe Gauss was crazy or somehow, or someone who was playing with it, and they just ask the question: what happens if I square the standard normal and add them together, right? And add them together. So let's say when we have the standard normal z, that I take a zi, and I told you that zi follow a normal distribution. You give me a moment. I change the function of the pen because it's creating a problem for me. Right, so let's say the pen, I want this one to be the eraser, nothing more. No. Shift right click others. Scroll pen eraser. Okay, good. Just that. Okay, thank you. Eraser. Now let me explain this one and then we do the simulation. So I tell you that z is a normally distributed between 0 and variance 1. Okay. When I say this, I give you a z. What is your expectation of the z value? 0. If I give you a zi square, what is your expectation of zi? That's the problem, right? Right. So let's say, why is this 0? So this is something you have to think. Now, if I give you a zi, the expected value is 0, right? If I give you zi square, huh? If 0 squared will be 0, but now it is not. It is 1. Because now let's think of how we compute the variance of a variable, right? You take zi minus z bar square, and you take the summation, right? I'm sorry, it is mu z, right? I mean the population mean, right? So, but this is it. If you want to take the variance, the sample estimate, okay, you take 1 over n. Is that right? Times all the values of zi minus mu. Mu z is 0, gone. So now it's the expectation of zi. But in this special case, my n is equal 1. But my n equal 1 doesn't matter. It's still a sample of 1, right? So its expected value will be equal to the variance of the standard deviation, the standard normal zi, right? And the variance of zi is equal to 1. Get it? Okay, so let's say that is the idea, right? Now let's say if I sum m times zi square, I equal 1 to m. Okay, I will have its name is a chi-square with m degree of freedom. So it depends on how many times you add the standard normal. And now I come to the punchline. If m is small, let's say if m is 9, okay, what is the expectations of chi-square 9? What is it? 9, right? Because it's 9 times. But are you going to get a 9? No. It could be 90. It could be 4. And it varies a lot. Is that right? Why? Why? What is the size of the sample of the zi? 9. The sample is very small. So it will vary. Is that right? It will vary. Now, when the sample is large, the randomness cancel out each other. Is that right? And you will get, if the sample is 9 million, you will get that the value of the chi will be very much likely to be very close to 9 million. Is that right? Because when the sample size gets large, the randomness cancel out. Is that right? So let's say to do that, you do this for me. First, you generate a chi-square, okay, of 5 degrees of freedom, of 20 degrees of freedom. You graph them into one single graph. Okay, let's do that and practice with the skills of graphing a chi-square, right? And then we will talk about now. And immediately after that, your task is to show me and explain to me by Python why is it that the t distribution approaches the standard normal when the sample size is large. All of these things you already know very well, right? In your econometric courses. Remember that? So now you demonstrate that in Python. That is programming. Right? Okay. So 2 things I need you to do. One, simulate the PDF of a chi-square with different degrees of freedom. Okay, that's the first one. Okay. The second one, show that t approaches normal 0, 1, tm as m approaches infinity. Okay, so what is a t? Now let's say, just for the sake of being quick, if you guys have forgotten, what is a t? A t is the ratio of a standard normal divided by. What is a t random number? Don't remember either. Okay, now let's say a t is defined as a standard normal zi divided by chi-square m over m. Is that right? This is a definition. Is that right? Now, ladies and gentlemen, just have a look here. Just have a look here. When m goes to infinity, what is the value of chi-square? Now, forget about this. When m approaches infinity, what is the value of chi-square? M, right? M divided by m, what do you get? 1. So t is equal to zi divided by 1. It will be ci. That's why when the sample gets large, you get t that is the t distribution approaches the standard normal. The reason behind, right? Show that in your Python. Okay. 2 things. One is to show different the behavior of the chi-square with different degrees of freedom. The other is to show graphically that the t approaches the standard normal when the sample size gets large. Okay. Because now we are going to compute the t. Let's say this is a little bit of probability that you can play with. Okay. One of the fastest way is to take a picture of that, post on ChatGPT, do it. It will do quickly, right? Or type that into ChatGPT. Ok không các em? Sau mình compute mấy thứ này, xong mình chuyển sang cái simulation của cái law of large number, đó là mình xong cái regression. Now, what is the question that the task that you have to solve now? What is it? Now, let's say the task is to one is to write a simulation, right? The other is to demonstrate this. So Khiết Anh, you are doing something else. You are computing the t statistic, right? Fine, fine, but we already done that, right? We already did that. So can you do this? I mean, that's quick. Quite it can be done quite quickly, right? Good. Là Ok, các em làm được chưa? Nhanh thôi mà đúng không? Vào chat GPT. Ok, nào. Generate 10 chi-square uh, 10 chi-square chi-square PDF of TF file 2. Okay. I have just reinstalled my Windows. I think there is a function somewhere that keep notifying something. Yeah. Okay. 10 chi-square, the degree of freedom, let's say 4, and let's say 1, 5, 10, 20, 30, and 50, right? Chi-square PDFs. In a one single diagram. Python, using Python, right? Using Python. It misunderstood me and give me just all of the graph, right? So I say, give me Python code. Okay. Well, that will be very quick and very simple, right? Control new, Control A. I paste it here, and just keep running. I will get the graph here. And get the graph here. So the question to you all is to explain why that when the sample size gets large, so let's say the chi-square will approaches the normal the normal distribution. That's because of the law of large number, right? The law of large number. So in this case, you see, so this is the way that it will be done. Very simple, very fast. The only thing that we need to know is, what do we want? We want to show the graph of the chi-square, and just ask as prompt that in ChatGPT, we will get it quickly, right? We will get it quickly. So not a lot of challenges here, right? Not a lot of challenges here. But let's say now you understand why it has this shape. Of course, when most of the probability focused here, right, concentrated here, you see that it's very high. This is the reason why the distribution of the PDF of 50 of a chi-square with 50 degrees of freedom just is shifted to this one. But let's say basically when it is there is only 1 degree of freedom. Every time you generate a standard normal, what is the closest what is the expected value? Somewhere 0. You square it, it will be even closer to 0. That's why most of the probability will be here, right? This is the idea. But let's say if you have more and more standard normal, some will be 1, some will be 3 sometimes, some can be -3 sometimes, very rare, but sometimes it happens. And then you square them all, you sum them together. They will be more or less equal to the total, the sum of 1, the number of degrees of freedom, right? So this is the reason why you would have that. Now, so can you simulate, can you give a, let's say, the steps here is like, if you ask it to be, if you prompt in ChatGPT to get this task, you sit down, pay attention to it a little bit, you will see that, so basically the steps are quite human, right? Firstly, you define the degrees of freedom. Then, what is the linear space here? So you have a line, and you will ask ChatGPT to divide that line. The line starts from 0 to 100, and divide the line into 1,000 points. Okay, so this is linear space. So sometimes you have to draw a graph. You must have the unit on the horizontal line, right? So let's say the command here is to say you use NumPy. You will create 1,000 points that spread from 0 to 100. This is what you get. Okay, so Python will start from here. Okay, calculated 1,000 point here. For each value of each PDF here, it will calculate the value of the PDF. And then it just graph the value of the PDF against the axis. Nothing more, right? Okay. That is what you would get, right? So let's say, now if we want to say, now I want to demonstrate the fact that the t distribution will approach the standard normal as the sample size increases, we would just simply write. So let's say, give me Python code to demonstrate that the t distribution approaches the standard normal as the sample size goes from 10, let's say 10, 20, 30, 50, 100. Now, so let's say if I do this, it will give me a list of graphs, right? And then they will be in a single diagram, and sometimes it is quite jammed, right? So let's say if we do that, we will understand. Okay. Good. So you see that it will give us a graph that this is the dashed line is the standard normal, and you see that it approaches the standard normal. But if you act in this way, it will be very difficult to see, right? So let's say we can prompt it in a different way. We say, let's say, let's demonstrate the property by separately combine H, T, M with a standard normal, and give me different diagram, right? If we say that, so the purpose is to show something that I gave you in the slide, right? To show something that I gave you in the slide. So basically, the idea is when the sample size is 10, you see that the standard normal is the red one. The t distribution has a thicker tail. What do we mean by thicker tail? So when we have a thicker tail, the tail is more likely or less likely? More or less. Now, when we have a thicker tail, the probability is larger, high, more likely. So let's say when you see that when we have a small number of degrees of freedom, right? The probability density of the t is higher here. So the density, probability density indicates how likely it is. So it is taller than standard normal. So it is more likely, right? But if it is taller here, then it must be shorter here. Because in the end, the total area under the two curves must both be equal to 1, right? And it is also thicker to the right, indicating that it could be more likely to be extreme values, right? But as the sample size approaches, let's say 50, you can hardly distinguish between them. And when it goes to 1000, it's more or less the same. That means if you take a chi-square with 1000 degree of freedom, what is the value of the chi-square? 1000. Most of the time, it will be 1000. So you take 1000 divided by 1000, you have 1. It approaches the standard normal. Is that right? So again, I often make fun of students who say, I'm learning Python. I would say, what do you learn from Python? Either you have to learn about writing something, econometrics, math, programming, some kind of computer science project, right? But you must have a goal in mind and the knowledge. And you just use Python to demonstrate the knowledge that you have. And when you know what you want, you will know how to program with the help of ChatGPT. Okay? So these are just simply the idea, and please be with me and try to develop a kind of sense about the meaning of the law of large number. What is that? That is to say, when you randomly draw any phenomenon in life, it will always contain some randomness. But if your sample goes large, the randomness cancel out each other, right? And then you will get what, and if you take the average, you will get what is the true population value. Get it? So that is the idea. So the reason why I talk about this one and also the chi-square is to demonstrate to you guys how important it is to understand the idea of the law of large number. So if you understand it, you can explain many things that you have studied so far, right? So when you talk about the law of large number, when you say that if the sample size becomes large, this happened, that happened. If the sample size becomes large, you don't even need. Okay, let's talk about this is some point. Then we say that when the sample size becomes large, you don't need the error term to follow you don't need the error term to follow a standard normal, a normal anymore. As long as it is IID, right? As long as it is IID, then the estimated beta won't follow a normal. Okay, that's also follow from the so-called the central limit theorem. We are not going to discuss it here, but say the idea is to demonstrate that value, right? Good. So with that, I think it's better that we should go on with the p-values. Okay. So what do we mean by the p-values? Okay. Now we understand the t. We know that the t approaches the standard normal. Let's move on with our regression. Now, so let's say, what is the p-value? Now we are already expert, right? So the p-value can be explained in different ways. But let's say in any hypothesis testing, you would have the null and you have the alternative.
Yeah.
The p-value is the probability that you are wrong if you reject it. Full stop. Okay, right? So that's something we already know, right? So how to get the p-value? Okay, how to get the p-value? So let's say from now on, if you want to talk about the probability distribution, remember there is a library called SciencePy, and in the SciencePy, if you have the stats here, you could have the t, you could have the normal, you could have the chi-square, you could have the Weibull, and all kind of distribution in the f and the like, right? So this is where you can get it from, right? So how can we compute? How can we compute let's say, how can we compute the p-value? So when, let's, for example, we assume that our random number follows a t distribution, and for some reason we get the t that is here. Let's say, let's, for the sake of demonstration, we put that the t equal to -2. Okay, we say that it follows a t distribution. We compute it. It is equal to -2. You will start asking the question whether this is an extreme value. If it is, let's say, can it be the case that a t value, a certain statistic follow a t distribution that could be equal to 2? If you say no, this is not possible. I accept that I can be wrong, but I don't believe it. So I reject the no. I said the statistic cannot follow the t. If it cannot follow the t, then the no is wrong. And the no is wrong. So I reject the no. Okay? So when I say that this is extreme, I am accepting the fact that it could be even smaller or even larger. But in my view, that is extreme and I reject it. Right? So in that case, you can be wrong this part of the time and this part of the time. Right? So in order to compute the p-value, we must be able to compute the probability here and the probability here. Right? Without Python, no way. Remember those times we have the big thick book with the distribution table and try to go back to it? Now we don't do that, right? But let's say how to get the p-value here, right? How to get the p-value here? It is this is what I already did, right? So the p-value I calculated in this case is equal to 2. Now let's have a look here. To 2 times 1 minus the CDF of the absolute value of the t statistics. Why is that? Right? So let's no. As long as we understand the logic mathematically and the reasoning behind, coding is just a piece of cake. Right? So let's say this way. So I want to know how likely certain thing is. If I get a t value equal to -2 or -4, I would calculate the area from infinity and -infinity to here. If this is the CDF, right? This is the cumulative distribution. Okay, so when this is minus, it's easy because I can immediately compute this one times 2. It will be the probability of the p-value. What happens if I get a 4? If I calculate the CDF of the 4, it will be almost 1. So when it is 4, I have to calculate the probability that it is larger than 4. Is that right? So I would take 1 minus the probability. So it is two things at the same time. Either you get a -1, you take the cumulative distribution value, function value, times 2. That is the p-value. If you get it larger than 1, larger than 0, you have to take 1 minus the cumulative. Oh. Okay. So in this case, there is a way to do it. Let's be very consistent. If it is negative, take the absolute value. Fair enough? You take the CDF, because if it is here, you take the absolute value and zoom it. And let 1 minus the CDF, you won't get the probability. So you don't care whether it is positive or negative, because it is always positive, right? So this is the idea that Python suggested. So let's say the p-value is 2 times 1 minus the absolute value. In order to compute the absolute value, you need to add the NumPy function, a NumPy library, and in that you need the absolute value function. You put the number in. Okay, of course you have to indicate the number of degrees of freedom here, right? And then you can compute the CDF. Take 1 minus the CDF, you have the upper part. Times 2, you have the p-value, right? So this is, so sometimes learning Python is, you know how things could be computed. You eyeball. What do I mean by eyeball? You look at it for a long time. I'll see, this is how we can communicate with Python for that message, right? So if you don't do the eyeballing, you will forget everything after the course. So my message to you is to sit down and have a look at it, right? Have a look at it and try to get used to it, right? Of course, we have the R square. R square. Now I won't do it once more, and then we may have to move quickly, right? Now let's say the R square. The R square. How to compute R square manually? Oh, come on. How can we compute R square manually? The R square can be defined in 3 ways, right? In 3 ways. One is that it is the square of the correlation of the predicted value and the original value. That can be proved, right? Can be proved down here. Or it is, this is easy. 1 minus the ratio between the total sum of square of the error term and the total variation in y. What is M1 here? I think we must know it a lot. What is M1 here? The mean, right? The mean, right? So right, so you have the this is the residual maker, right? When you have only one constant in the explanatory variable, right? So what does it do? It will. So why do we need to do mean? Because whenever we compute the correlation, the covariance, and the like, we will always have to calculate the deviation from the mean, right? The mean is the deviation from the mean. So in this case, it could be this one. This is the total variations of the dependent variable. This is the part of variation that cannot be explained. Okay, so 1 minus this one is the part of variation that can be explained. Nothing more, right? So 3 ways of computing the R square. Please do that. You have 5 minutes to do it. Right. Okay, can you do it? And then just so now you have the steps, right? Whatever you want to compute, you need to know the mathematical derivation of it if you want to compute. Otherwise, what are you going to learn with programming? Programming is to write in the Python's language what you know. Okay. Yes. Oh, okay. Good. What's the question? Mhm. Okay, so let me explain. Sometimes we do not know. Let's say we hypothesize the value of beta total income equal to 0.9, but we do not know whether it is less than 0.9 or more than 0.9. So if it falls to the left of 0.9 and you think this is very active, then when it falls to the opposite side, that is larger than 9, you will also, this is active. So if you reject one side, you assume that the other side is also active. So in that case, you have two-sided test. Okay, two-sided test. So you decide, you do not know whether it is to the right or to the left. So it happened to the left, and you conclude that this is too active. Next time, if it is on the right, you will also reject it. So in the symmetric test, if you reject it on the left, you also reject it on the right. So that means it is two-sided. Sometimes you know that it is either larger than or smaller than. You know very well. For example, if you want to, so let's say if you talk about the chi-square, right? The chi-square. Now let's imagine we are talking about a chi-square. The chi-square. Let's think of it in this way. The chi-square, right? So if you get a chi-square number, it can only be smaller than, or if it is here, it is not symmetric. So if it will never be zero if your chi-square is large, right? But if it happened to be here and you say that this number is too large, so it cannot belong to the chi-square, then you will be wrong from here and up. It is one-sided. Yeah, but it cannot. You say that if it is from here up, it is too extreme. Then opposite to the other side, that is, let's say this is 100 minus 100. If it is smaller than minus 100, you will say that it is too extreme. But the chi-square can never be negative, so it will never happen. So you only care when it is larger than this one. It is one-sided. Okay. Sometimes it can also be the case that you know certain coefficient follow a t-distribution, but you know that it is positive. Okay, if it is, so you know that it will never be negative. So let's say if you have a t-distribution, but you know that it is positive, so it can only be from 0 and up, but it shouldn't be too large. So now it happened to be here, then you ask yourself the question, if I reject it, what is the probability that I will be wrong? It will be only this part and up. Get it? This is the idea of one side or two-sided. But that's the knowledge is, this is not an econometric course, right? So let's say we get the intuition, so we fit into Python, right? Now can you all compute the R square? It will be quite easy, right? Now please compute the R square and then we have a break. First method là thầy có first method, second method. Bây giờ ta biết nó là cái gì thì ta cầm vô được đúng không? Mày thầy xem ra như thế nào. Đâu? À, em vừa lấy từ ChatGPT hay em tự code?
Em hỏi từ cái formula xong em mới nói nó.
Ok, bởi vì em đang làm rất rất giống như trong slide. Không thì hỏi vậy thầy tưởng em mà code được nhanh như vậy lúc giờ thì chắc là cũng cấp thành siêu nhân rồi đấy. Nhưng mà em có hiểu các cái này không? Đến bây giờ tức là bây giờ là nó code cho mình là mình sẽ implement ngay được đúng không? Đấy. Vậy thì quan trọng nhất của cả khóa học này thầy chỉ gửi đến cái thông điệp đó thôi. Em định làm cái gì? Hiểu không? Rồi sau mình làm một số thứ mình quen đi. Đến bữa sau là sang đến cái phần mà xử lý về dữ liệu. Trong đầu mình có một cái research question và mình phải compute cái biến đó. Thì mình đã biết trước trong đầu mình là mình cần cái gì rồi. Đúng không nhỉ? Đấy. Thì hôm nay mình đi tiếp một số cái này nữa. Chủ yếu là bây giờ các em phải chịu khó làm như Đan Thư vừa làm đó, rất nhanh. Cái công thức toán là như vậy, implement nó vào trong Python đúng không? Thì sau đó là mình có thể hiểu cái mục tiêu của nó. Yes, we should have a lunch break now. Thank you. We will come back at 1 sharp and I have to be very quick in the afternoon. I will go quickly and talk about the F test. In the afternoon, I will talk about something that is quite theoretical. I will show you how all kind of tests that we have done so far. The LR test, the test, and the whole right? So let's say let's be familiarized with this one because you use all the time, and most of the time you just take it for granted. So today, the message or the approach that I'm taking is you know what you want to do. So and let's say to be very pragmatic, I want to prepare you also a little bit for empirical. You need to know all of these things in a colorful way. Hey Linh, hello Linh. Shield already left. Not yet. Hello Linh, let's have a lunch break, and then we come back at 1, okay?
Dạ.
Bye bye.